Next, I'm going to talk about continuity. So continuity means in lay terms that I can draw the graph of a function without having to lift my pencil, right? So like lines are continuous functions, cubic functions are continuous functions, and sine and cosine functions, right? Those are continuous functions. So polynomials are rational functions and trig functions are continuous at every point over their domains. So let's take a look at this. X plus 1 over x plus 5. Is this continuous at every single point? No, right? Here, my domain is not every single number, so I have to edit it, right? What's not in my domain? Negative 5. So it's going to be continuous from negative infinity to negative 5, union negative 5 all the way to infinity, right? Same thing is true for this rational function, right? Here we are continuous so what are two values that can't be in my domain? 2 and negative 3. So I'm continuous over every single point in my domain, and what I'm writing over here are the domains. Here, this is continuous from negative infinity to positive infinity. Same thing with this lovely sine function here. Now, let's let f of x be defined on an open interval containing x equals c. F is continuous at x equals c if the limit of f of x equals f of c. If the limit does not exist, or exists but doesn't equal f of c, we say that f has a discontinuity or is discontinuous at x equals c. So this top graph is discontinuous at a, right? If I'm approaching my limit from the left, it's not the same as my limit from the right, so my limit does not exist. In this case, my limit does exist, right? So it is continuous. So how do we prove something is continuous at a point? These three conditions need to be satisfied. 1, f of a is defined. 2, the limit as x approaches a, f of x exists. And the limit as x goes to a of f of x is the same as f of a. So this is how we'd show discontinuity. Continuity. It's discontinuous if it fails any of these keys to be continuous. So here I have to determine if the following functions are continuous at a given point. So I have x minus 2 x minus 4 squared over x minus 2 at x minus 2. So I'm going to figure out. So is f of so for first thing I need to know for clause 1 is f of a defined. If I plug in f of 2, well, I get 2 minus 2, 2 minus 4 squared, right? I'd be dividing by 0. So this function is discontinuous at x equals 2 because f of a is not defined. This is discontinuous. Now let's take a look at this piecewise function at x equals 3. So first, is f of a defined? Yes. Let's find what f of a is. F of a, which is 3, equals, here's the equation where 3 is divided, negative 3 squared plus 4. So I have negative 9 plus 4, which is negative 5. There's f of 3. Next, I need to know, does the limit at f of a exist? So I need to know what the value is approaching from the left, right? So if I take the limit as x is, this is x is greater than 3. This is coming from the right. That would give me 4 times 3 minus 8, which is 12 minus 8, which is a positive 5, right? So this is discontinuous at a point because this limit as x goes to a of f of x does not exist. All right, next case. Let's say f of 2x plus 1, f of x is 2 at x equals 1, and negative x plus 4 is at when x is greater than 1. Okay? So is f of a defined? Yes. F of 1 is 2. Okay? Does the limit as x goes to a of f of x exist? Well, let's take a look. My limit as x goes to 1 from the left, from the right, so when x is greater than 1, is going to be negative x plus 4. So my limit is as x goes to 1, I have, my limit is 3. And then if I do my limit from the left, I have 2x plus 1. Okay, so my limit also is 3. Very cool. Okay, so right now I have the limit does exist. The limit is 3, but wait, my limit doesn't equal f of a. So this is still discontinuous. So there are 3 different types of discontinuity. There's removable discontinuity. Okay, that's when there's a hole in our graph. So for example, we just didn't define when x equals 3, right? There are jump discontinuities. That's what happens in a lot of piecewise functions. And then there are infinite discontinuities. That's what happens when there is an asymptote. So let's take a look. Here's the formal definition of these discontinuities for your references. So let's figure out the types of discontinuity. So here I have x squared minus 4. We've seen this before. This discontinuity is a asymptote. So it is a infinite discontinuity. Here we have a jump discontinuity. And here we have another infinite discontinuity. Now let's actually take a look back at this because I think I might have made a mistake. So I can factor this out, and that would leave me with f of x equals x plus 2. So then the limit here does exist, and it's 4. So here we have a jump discontinuity. No, sorry, a removable discontinuity. A function is said to be continuous from the right if the limit as x approaches a from the right is f of a. A function is said to be continuous from the left at a if the limit of as x approaches a from the left of f of x equals f of a. Okay? And a function is continuous over an interval. It is continuous at every point on the interval. A function is continuous over a closed interval if it's continuous at every single point in a and b and is continuous from the right and from the left. We could also have a function continuous over the form parentheses a comma b bracket, where parentheses mean the endpoint is not included, and the bracket means that the endpoint is included. Okay, so let's take a look. Now here I have f of x equals x plus 3 over x squared minus 4x. Now remember that this is a rational function, and rational functions are continuous over their domains. So let's determine its domain by factoring the denominator and setting it equal to 0. So I have that x equals 0 is not my domain because that would make us divide by 0, and x equals 4. So my domain and the intervals there, this would be continuous are negative infinity to 0, 0 to 4, and 4 to infinity. So it is, this function would be continuous over each of these individual intervals. Now I have the square root of x minus 3. Okay, so let's go ahead and take a look at this. I have to figure out what this graph kind of looks like. That's what I like to do. Remember, rational functions, their graphs kind of look like this. So I know that this graph is shifted to the right 3. Okay, so my graph is going to look something like this. I could have figured that out by setting it equal to 0, right? X minus 3, 0, x equals 3. So my graph is continuous from 3 all the way to positive infinity. And remember, infinity always gets a parentheses. Last but certainly not least, I have the square root of 4 minus x squared. Okay? And this is continuous from negative 2 to positive 2. And here's why. Because if I plug in a number bigger than 2, like 3, this becomes an imaginary number. So this is going to be continuous from negative 2 to 2, and here's why. Because the limit from the left, is 0, and the limit from the right is 0. Let's talk about composite functions, right? Remember, that's where I would write f composed with g of x, right, which is f of g of x, right? We're substituting in a function for x. So if a function is continuous and if two functions are continuous, then if I take the limit of f as x goes to a of g of x, that's the same as pulling the f out, right? So I'd really have f of L. So let's let a equal 4. So, quick thing I want to do is I want to make sure that f of x is continuous at 4, which it is, right? And I want to determine what the limit as x goes to 4 of g of x is. So I'm going to take the limit as x goes to 4 of negative 3x minus 1, and that's going to actually equal 13. Sorry, negative 13. So f of g of x equals 1/2 negative 3x minus 1 plus 2. So I have negative 3/2 x plus 3/2. Now the limit as x goes to 4 equals negative 3/2 of 4 plus 3/2, which gives me negative 12. Halves plus 3/2, which is negative 9 halves. Now I want to show you that this is the same as if I had done it this way, which would be 1/2 the limit as x goes to a of g of x plus 2. So 1/2 times 13, that gives me 13, negative 13 halves plus 2, which equals negative 9 halves as well. So you would get the same answer. Next, remember that trig functions are continuous over their entire domains, okay? So you would also be able to do that for this problem as well, okay? This is a composite function.